Hello, welcome to the second video on sampling plans and their corresponding operating characteristic curves. We are going to continue our discussion on the already computed table, and then we are going to do operating characteristic curve for a double sampling plan. This is where we left before, and you can see the operating characteristic curve. If we explore the data, let's make it a little more readable. We explore the data. You can see that if in our plan, remember this is our sample size n, and this is the proportion of defective. This is the entering quality of the product into this just before the sampling process. And if we have a sample size of 30, let me zoom in. If we have a sample size of 30 and the proportion changes from 1% to 12%, at 30 we would accept 99.67% of the lots if they come with 1% defective. Maybe we want to be more stringent than that, and if that is the case, with 1%, and this is with C fixed at 2, we may need to change the value of C. That information is behind this chart. Let's find the room so we can do this. Okay, this is a little better. And our model right now has an acceptance number C of 2. We can leave that fixed, say for instance at 0, and that will change the table. And now at 0, with a sample size of 30 and an incoming quality of at the moment of sampling of 0.1%, it is 74% chances if of the lot being accepted if the sample size is 30 and the proportion of defective into the sampling process is 1%. So we can control the level of alpha if we are willing to live with 1% by changing the acceptance number, and with 1% and with an acceptance number of 1% and sample size of 30, the value now, the probability of acceptance, is 96.4. And the negotiation with the beta error would be that with 12% of defective, we would only accept about 11%. If we are not satisfied with that, we may want to maybe increase the sample size. Right now is 110. If we increase it all the way to 40, is 0.039. We don't have to increase it all the way to 40. That's why we have an Excel spreadsheet, so we can explore different values. So maybe 35. And that gives 6.6% at 12. And we can look for a value that that gives us a level of adequate both beta and alpha. With 35, our probability of acceptance is 95%, and maybe that's a number we would like to consider. In the previous video, we obtained 36 because 36 was exactly 95%. So that's how you can design your sampling plans. This is statistic based. This is independent of any other model or the nature of the product. This is just binomial distributions, and it works for everything that that you would like to use sampling plans for. Now I'm going to construct an operating characteristic curve for the case of a double sampling plan. These will have to consider the possible options on the combinations of what may happen as we go selecting the samples, and depending on the outcome, we will decide what would be the next step to take. So let's see. First of all, I decided that the proportion of, I want to model the proportion of effective of 1%. The sample size on the first sample is 30. The sample size on the second sample is 40. The acceptance number in the first sample is 1. The second sample acceptance number is 3. That means that if we get 1, it gets accepted. If from the first sample, if we get 1, it would get accepted. If we get 2, we go to a second sampling plan. If we get 3, we go to a second sampling plan, and if we get 4, it will be rejected. And we have to consider the possible outcomes in the second sampling plan, in the second sample. So let's see. We compute the binomial distribution for the first sample. The number of successes is 1. The number of trials is 30. 1 is the acceptance number. 30 is the sample size. The probability is the proportion of the effective. And we want cumulative because we would accept with 0 or 1. And that binomial distribution is 96.38. And in that case, we would accept it immediately. Now, in case that it's more, we need to consider the case in which we may have, what if the number drawn was equal to 2? What if the number drawn was equal to 3? Because those two considerations would include the possibility of being accepted at the second attempt. So we have to compute those probabilities as the binomial distribution, with the number of successes now being 2. Number of trials remains 30, and the probability remains 1%. Well, I'm going to use reference cells so I can change those in case I want an analysis. Number of trials 30, probability 1%, and I don't want the cumulative because I am not interested in the possibilities of 0, 1, and 2, only when it gets to 2. So it's 0 here. Now, this is referenced into cell number 2, or I2. So that's the probability. And the same case would be when x equals 3. This is the binomial distribution with 3 successes, sample size 30, proportion of effective 1%, cumulative no. Now, if we have number of defects found in the first sample, we can still have one more defect found in the second sample and still would pass. What is the probability of that happening? We would consider, if we use binomial distribution, that the number of successes that are of interest is 1 with trials, well, to make it parametric, binomial distribution, and the number of successes is the difference between 2 and 1, 2 and 1, with the number of attempts or number of trials is 40, and the probability remains the same. And we want the cumulative because we would accept if we have 2 in the first one and 0 in the second one, or 2 in the first one and 1 in the second one. So both 0 and 1 would be accepted in this case. And the joint probability distribution for this would be, well, if it's 2 in the second times 2 in the first sample and 0 or 1 in the second, the probability of that happening is 3.08%. Using the same logic with x equals 3, this is in the first sampling process we obtain 3 defects. Now we have to have exclusively 0 in the second in order for us to be able to accept the plan on the second sample. So we compute the binomial distribution with the number of successes being 3 minus the acceptance sampling number 3, and the number of trials is the second sample's number 40 with probability 1%. And here it doesn't matter if it's cumulative or not because it's just one term, but let's just use 0. Okay, now the joint probability of these two is the probability of obtaining 3 in the first sample times the probability of obtaining 0 in the second sample, and that answer is small number, less than 1%. And the total probability is now the summation of being either accepted in the first attempt or accepted when x was equal to 2 and certain parameter, and obtaining 0 or 1 in the second sample, or when the first sample was equal to 3 and obtaining 0 in the second sample. So that number now is 99.6. And now we can create a sensitivity analysis. Let's say that we fix everything except N1 and the proportion of defectives. So in the corner we put this probability of acceptance, and we're going to use N1, the possible values for N1, maybe 20, 30, 40, and 50. And the possible values for the proportion of defective on the way to 12%. This is the proportion of defective. And we can select our data table. what if analysis. The top row is associated with N1, and the proportion of the effective is on cell E4, and this is the operating characteristic curves. Of course, I can make the nice graph. I'm going to copy that here. And creating the graph for our curves on a double sampling plan. So with a lot of effort, we can completely customize these and make the rationale of what should be the size of N1 and N2, but at least you have the tool, and it should be way easier now to do the selection of N1 and N2 and the acceptance numbers on a more complicated multiple sampling plan. The book offers these same formulas, but it doesn't offer the automation through Excel. So here you have it, and I hope you find it useful.